Kia ora, and welcome to this Manaaki Whenua LINKOnline Webinar. I'm Christine Harper, Manaaki Whenua's Stakeholder Relationship Manager, and my job is helping to join the dots between our research and the questions that our stakeholders are grappling with. Characterising and understanding New Zealand's soils and how they respond to management is a key part of our work, and you will have heard about other soil topics in this series over the years. Mudge is the research portfolio leader for climate adaptation and mitigation, and his specialist area of research is soil carbon. This webinar will provide you with a taster of the range of work underway to better understand New Zealand's soil carbon stocks and how to measure and manage them. I'll be back at the end to help with questions, so don't forget to put them in the chat box as soon as you can. Over to you, Paul.
Kia ora, Christine, and thank you everybody for joining today. So today I'm going to talk about soil carbon, risks and opportunities in Aotearoa. I've only got myself up there as the author of this, but I do want to acknowledge that this is a team effort. Lots of other people have contributed, but too many to list here. Particularly want to acknowledge, I guess, the University of Waikato, who we work closely with on a lot of this work, and Louis Shipper did a presentation for NZAGRC a few months ago, which covered some similar material, and I've deliberately made this one focus more on the soil sampling, direct sampling, rather than the eddy covariance measurements. So just a quick outline of what I'm going to talk about today. I'll touch on the importance of soil carbon. We'll look at how much carbon there is in New Zealand soils, and then look at how to monitor changes in soil carbon at the national and also the farm scale, and then dig a little bit deeper into the effects of how land use and management influence soil carbon stocks, and then wrap up with a summary at the end. So why is soil carbon important? There's two main reasons. The first one is it's critical for soil health. It's really important for helping maintain structural stability, and that in turn then helps root growth, water and air movement, and infiltration. It's also the key food source for soil biota, which are then really involved in nutrient cycling, and soil organic matter is also a store of nutrients as well. And then what's very topical at present is that soil carbon also feedbacks with the climate via CO2 release or sequestration. So globally, soils contain about twice as much carbon as the atmosphere. So that any changes in the soil could actually have a big impact on atmospheric CO2 concentrations. And so therefore, this is a risk and an opportunity. A risk if carbon is lost, an opportunity if carbon is sequestered. So how much carbon do we have in New Zealand soils? What we did is, what Stephen McNeil did, is compiled all the available data that we have, historical data, and then developed a spatial model and a map. And you can see that map on the right-hand side over here, and you can see that there's quite a lot of variation in soil carbon across New Zealand, quite high carbon stocks on our nice allophanic soils, volcanic soils in the North Island, and high carbon in our peatlands in the Waikato and in Southland. And on average across all of New Zealand, we've got about 90 tonnes of carbon per hectare in the top 30 centimetres. That's higher than Australia, South Africa, Brazil, the US, or France. And so I guess the quick take-home message from this is that New Zealand has a lot of soil carbon, and we really want to maintain what we've got. We don't want to lose it to the atmosphere, and if we can, it'd be great if we could further increase the carbon that we have. And just a comment here that this map is currently being updated by Pierre Raudia, who is bringing in a new modelling technique and a lot more data that's been collected since this original map was made, plus more historical data. So we should have a new soil carbon stocks map not too far away. Pierre's just finished one on carbon concentrations. So in New Zealand, we actually have an existing monitoring or modelling system for determining for our national inventory reporting for how soil carbon stocks change. And it's a statistical model, and it's developed following standard IPCC methods. And it predicts changes in soil carbon stocks associated with changes in land use. And this figure here just is a summary of some of the classes. So we've got change in soil carbon stocks here on the y-axis, and the reference used in the model is low producing grassland. And you can see that if you go from low producing grasslands to any other land uses here, you actually get a loss of soil carbon from the mineral soil. Obviously, in these forest classes, you get an increase in above ground biomass in that. But our grasslands have the highest carbon stocks in our mineral soils, in the soils. So this model is pretty simplistic, and it is based on a number of assumptions, such that if a land use is converted, land use changes from one to another, it'll reach a new equilibrium after 20 years. And it doesn't account at all for management within land uses. And it's also based on data that's collected way back to the 1960s, and often for other purposes. And it's not fully representative of New Zealand's agricultural land. And until recently, there was no system directly measuring changes in full profile soil carbon stocks for agricultural land in New Zealand. But that has changed recently because we've now got a new benchmarking and monitoring system for agricultural land, and this is funded by the New Zealand Agricultural Greenhouse Gas Research Centre. And in this project, we've got about 100 sites in each of the 5 broad land use categories shown here, to give a total of 500 sites across New Zealand. Now, the sites have been randomly selected within each of those land use classes to try and make sure we get a representative and unbiased sampling across those land use classes and agricultural land in general. And sampling at all of these sites is to 60 centimetres depth, and sampling them on a 4-year rolling schedule. And the aim is to have the benchmark sampling completed by 2023. And then by 2031, we should have taken samples for 3 sampling times from all of these sites. So far, we've done 292 sites of the benchmark sampling, and that's continuing. Just point out here that the current study is designed for the national scale. There is potential to add more sites through regional or industry initiatives. And so this project is focused on determining how much carbon, the carbon stock that we have, and then whether or not it is changing through time under these different land use classes. So it's focused on the soil carbon stocks. We have actually got aligned research, one with an European soil collaboration that Aotearoa is leading, where we're looking at the types of carbon in this soil and the stability of that carbon. And Sam McNally is also analysing some of these soils to look at the vulnerability to loss and also the different carbon fractions in these soils. So digging a little bit deeper than just the soil total carbon and nitrogen stocks. We've also recently done some work for MPI where we designed a system for benchmarking and monitoring soil carbon stocks on individual pastoral farms, and we completed a technical report for that. And it uses a very similar approach to the national scale system. We've divided the farms up into land management units based on farm environment plans, because that's so it's common to what is a lot of farmers in New Zealand are having to do or will have to do in the very near future. Again, random allocation of sampling sites across the land management units, and there's an example shown in the figure here. And the same soil sampling and processing protocols as the national monitoring system. And there's quite a lot of interest in this at present. We get quite a lot of requests from people saying, oh, can we do this in New Zealand? And we can say, yes, the methods are there. We know how to make the measurements, but we're very careful to point out that we definitely can't guarantee that there will be any increase in soil carbon. And in New Zealand, unlike Australia, there is currently, I guess, no government mechanism wherewith farmers could be rewarded for any change or proving that they have had a change in soil carbon associated with a change in management. So now I'm just going to move on from the kind of detailed monitoring to look at the specific effects of different land uses and management on soil carbon stocks. And just the first one here is work that we've already completed, where we sampled from a number of long-term field experiments. And just a couple of examples, long-term superphosphate applications and across 4 sites had a massive impact on pasture production and animal stocking rates, but actually had no effect on soil carbon. In contrast, the long-term Winchmore irrigation trial, irrigation increased pasture production and animal stocking rates, but there was actually substantially less carbon under the well irrigated treatment compared to the dryland treatment. And I'll touch on another study related to that shortly. We've also done a lot of sampling using the paired site sampling approach. And one that was done in association with master student Alice Barnett at the University of Waikato. We looked at paired dairy versus sheep and beef pastures, 25 sites in the Waikato, and we found marginally lower soil carbon in the topsoil. And we've also looked at irrigated versus dryland pastures, and I'll give a brief example of that soon, and maize cropping and pasture, and I'll give an example of that as well. And we've also done more detailed work around paddock scale experimental manipulations using a range of techniques, but eddy covariance is one that I'll show an example of a mixed species swards. We're going to look at grazing management. I'll then touch on peatlands and then a new project on trees in the landscapes. So just a quick snapshot of the study on the impact of irrigation on soil carbon and nitrogen stocks. This is the study design here. We had dryland areas, unirrigated and irrigated areas, and we tried to find those in the same paddock, although that wasn't always the case, but the majority were. And we took 9 soil cores from each of these areas down to 60 centimetres, divided into 10 centimetre increments, and analysed it for total carbon and nitrogen. And we did that at 124 paired sites across the country, and you can see the distribution here from the Pumice, Reparoa, Galatea, through to central Otago. And the interesting thing was that on average across all of those sites, there was 5 tonnes less soil carbon under the irrigated than the adjacent unirrigated pastures. And there's a couple of papers that we've published on those. A very similar study design in the Waikato, where we looked at 41 paired maize and pasture sites. And so here we have the difference on the y-axis in carbon stocks per hectare between those paired sites, and here we have the duration of maize cultivation. And on average at these sites, the soil carbon stocks were 18.3 tonnes per hectare lower under the maize than the adjacent pasture, and this matches with the carbon inventory, national inventory model that I showed earlier. So similar magnitude to that prediction, and also matches with the results that we're seeing coming out of the national soil carbon benchmarking program to date. So now just moving on to looking at those more detailed experimental manipulations and looking at paddock scale carbon and greenhouse gas balances. And here I'm just going to show one example of a mixed sward versus a conventional ryegrass clover pasture. This was at the Lincoln University's Ashley Dean Research and Development Station, and we had a mixed pasture in this area and a ryegrass clover pasture in this area, and we had the eddy covariant instruments sitting here, and I'll show an example of how they work in a moment. So this is the setup of those instruments, actually an older set, and it was over Lucerne in this case. And how they work is that when the wind blows across the land surface, it creates these eddies. And then those eddies transport gases between the atmosphere and the land surface, and then back up again. And the eddy covariance instruments sit in here and measure the concentrations and the wind speed in 3 dimensions 10 to 20 times every second. And then it can average those numbers to produce the net balance of carbon uptake or carbon loss. And we also quantify all the non-CO2 inputs and losses, such as silage inputs or exports and leaching, to be able to calculate the net carbon balance. And we've now got new instrumentation that can do this for nitrous oxide and also methane, so we can do the full greenhouse gas balance. So from this experiment, we found that there was 39% less nitrous oxide from the mixed sward. So the mixed sward in this case was only a 5-species mix, and the key differences were there was inclusion of plantain and Italian ryegrass clover. And so you can see the time is on the x-axis here, and this is cumulative nitrous oxide flux, and this is in tons of CO2 equivalents on this side. And you can see that through times there was definitely a less N2O from the mixed sward. And the same numbers, but now we have the cumulative net carbon balance for those two systems. And we can see that actually there was an increase in soil carbon. So you can see below the line here is a carbon gain in the ryegrass clover, but the mixed sward was about carbon neutral, which is interesting. And when you add them together, the overall net greenhouse gas emissions were actually higher from the mixed sward. So a key take-home message from this, and a very similar experiment was done in the Waikato by Aaron Wall and Louis Schipper and others, where they had a pretty much identical instrumentation over very similar treatment, and they found basically exactly the same thing, although slightly less reduction in nitrous oxide than what we observed in the South Island. And what this points towards is that any mitigation, this is just an example of looking at different swards, we need to consider the impacts of those mitigations on all greenhouse gas emissions, and because we want to know what the overall effect is, and we don't want to have unwanted trade-offs. We want to instead identify the synergies. I'm now going to jump into looking at greenhouse gas emissions from peatlands. And this is work that Jack Pronger has been leading in collaboration with the University of Waikato. So this is an intact peatland in the Waikato, an iconic peatland. And you can see here that it takes up CO2, but it also emits quite a lot of methane from the system. But overall, it is a net sink of greenhouse gases, which is a good thing. However, when it's converted and drained to grassland or cropland, it becomes a very large source of CO2 and also a source of N2O and a reduced source of methane from the system. Overall, the emissions from the soil from these systems is about 21 tonnes of CO2 equivalents per hectare per year. So it's a pretty big number. And And that comes out, if you do that for all of the peatlands in New Zealand, including the cropland peatlands, it's about 8% of New Zealand's net greenhouse gas emissions. And this is not including the methane and nitrous oxide associated with animals. So this number here, 21, you probably add 10 on to that if you put the emissions associated with the animals that are grazing on this system. So they are a large source of emissions from quite a small area in New Zealand. And so we need to consider, well, what can we do about this? We could potentially raise the water tables, and that might reduce CO2 emissions. There's also, Jack's been looking into alternative options for use of this land. Polluter which is wet agriculture. So that's actually potentially flooding at lots and not having grazed pasture, but some other crops, and there's some opportunities for that. And another opportunity is, well, especially in certain areas, should we be considering restoring them from back to where these natural ecosystems where they are actually going to be a net carbon sink? So some important decisions to make going forward in relation to peatlands. Now I'm just going to highlight our new MB program. The short title is Trees in the Landscape. And this is going to kick off in, well, I think start of October. And it's co-led by David Whitehead and Sam McNally. And so it's quite a broad program and looking at quite a lot of different elements, but the key focus is around carbon storage in biomass and soil carbon. And I'll show a slide of this in a second. I'll just point out that in this lovely photo here, it's a beautiful landscape. This is a farm I worked on for a number of years before I went and studied at the university. So the focus of this program here is, I guess, looking at the complementarity associated with edge effects. And you can see in this diagram here that on the edges of forests, the trees will grow better, or the edges of small clusters of trees will grow better, store more carbon. There's a grass production could also increase, and there's a hypothesis that soil carbon could increase as well. And so this is what David and Sam are going to delve into deeper in this MB program. So it's be very exciting to kick off into that. And here are their emails if you want to follow up about that. So just in summary, in general, New Zealand has lots of soil carbon. So it's imperative that we keep what we've got and where we can increase that. For the benchmarking and monitoring at the farm and national scales, we're going to put a stake in the ground for where we're at now. How much carbon have we got? And make sure, and that's a spatially representative estimate. We're then going to be able to determine, are changes occurring, and does this differ between different land use classes? We'll also get some information around why changes are occurring. And then this data will improve our national greenhouse gas inventory reporting and modelling. The effects of land use and management, the examples that I gave were not particularly positive examples. We actually found lower soil carbon under the irrigated pastures, long-term maize, as would be expected, and under the mixed swards than more conventional ryegrass clover pastures. Really need to emphasise that we need to consider the impacts on mitigations on all greenhouse gases. We want to avoid trade-offs and aim for synergies. Again, emphasising that our peatlands that are drained and used for agriculture are large sources of CO2 emissions. And we've got a couple of projects kicking off soon, trees in the landscapes, and we're also doing a bit of work on grazing management that will start soon. So there's a couple of exciting areas. And I just thought I'd finish with a slide that I've pulled together, just trying to depict a few of the areas that we're trying to work on. So on one scale, we're working at this national scale benchmarking and monitoring. We're looking at the vulnerability to loss of carbon from those soils across the national monitoring network. And then we want to be able to model broad scale land use and management effects. At the other scale, we're looking at more specific management interventions at the farm scale, and that's feeding into some detailed process-based modelling and scenario analysis, and we do quite a lot of that work, and I haven't emphasised that here. We want to then kind of bring all that together, think about how that responds to climate change, and then we really want to be able to accurately predict soil carbon stocks, so what we've got now, and then how things might be changing for any location in New Zealand, and that's for current land uses and then transitions in land use or management practices. So that's something that a lot of this work is building towards. And a simpler way of saying that, David Whitehead suggested this, is spatial estimates of the national soil carbon mitigation potential for New Zealand. And just like to finish with some acknowledgements here. And I'll leave those there, and I'll particularly focus on the bottom one, the many farmers that has allowed us access for sampling across the hundreds of farms that we've visited, and also those that have allowed us access for more in-depth studies. So thank you. Back to you, Christine.
Thanks, Paul. That's been really, really fascinating, and I recognise even from some of the questions that it's been a bit of a quick rush through some real areas that people have some more in-depth knowledge needs. A few quick questions. Paul, why does New Zealand have such high carbon levels in our soils?
Yeah, I think this picture kind of illustrates it a bit, is that we have a really good climate, lots of rainfall, lush perennial vegetation cover across most of New Zealand. So good rain, perennial vegetation cover, and also, such as in this photo here, we've got quite a lot of volcanic soils which have specific mineralogy that helps protect and stabilise soil carbon. So those are a few of the reasons.
Great. Now there's a question here about the national benchmarking. Do the 5 broad land use classes include forestry?
No. So this was focused solely on agricultural land. The reason for that is that forestry has already been sampled systematically previously. Both plantation forestry and our indigenous forests have already been systematically sampled, and so we can go back if desired to determine whether changes are occurring under those land uses as well.
Thanks. And a bit of a topical question with the NPS for highly productive land at the moment. Is there a link between soil carbon and land use capability?
I've actually never done that analysis. I suspect that most of our highly productive land would naturally have quite good levels of soil carbon. That's what, yeah. Although some of them that have been used for really long-term cropping, that may have been driven down a bit.
Something to look at in the future. And I think we can squeeze in one last question. Do you see any benefits or limitations of farmers monitoring soil carbon concentration as part of their routine soil fertility assessment?
It could provide an indication of what is happening on their farm, but if the question is about changes in soil carbon stocks, generally the consensus is that you need to also measure the bulk density of the soil, and you also need to sample a lot deeper. But 30 centimeters is kind of the recognized minimum sampling depth if you're wanting to quantify changes in soil carbon stocks, because you could get a change in percentage, but if you've actually you could get a change in percentage and not actually get a change in soil carbon stock.
Like many of these things, it's the devil is in the detail, and so understanding some of those areas is the stuff that that we're all about. I can see there's still a number of questions coming in, but we are out of time. So I'd like to say a big thank you to Paul, and thank you to everyone who has joined us today. It's been fascinating. Your questions will be answered, and we look forward to seeing you back here on another soil related topic in a couple of weeks. Watch your email for the invitation. Thanks, and bye for now.
Thanks, everyone.